So actually, this is the first work we did on this superfluid in uh, 2004, quite some time back, on Fermi gas of atom. And I cannot resist telling a small story about it. I was looking at matter at high density, namely the quark matter in the core of neutron stars. And in neutron stars, in quark matter at high density, it seems quarks are fermions and they interact through the QCD interactions. And there is an attractive interaction between the quarks. And if there are fermions and there is an attractive interaction, they can make pairs, BCS pairs. That's the BCS theorem. So there is superconductivity can be there in dense matter also. So in that context, I was looking at it, except that if you are trying to put it into neutron stars, you have pairing between unequal number of atoms because the quark charges are different and you have to maintain charge neutrality. So if you have up quark and down quark, they have up quark has twice the charge of down quark. So you have to have more number of down quark to have make charge neutrality. And this up and down can form the BCS pair. So this is a case of pairing between different population of quarks, okay, different number density of quarks. And when we are doing, I saw some funny behavior in their distribution functions. Sometimes they were behaving like superconducting. Sometimes they were following the normal matter. And I was quite puzzled by it. I didn't mention it. And I did mention to Prashant. And Prashant said, oh, this is very interesting. And by that time, there was a paper by Frank Wilczek and Elena Gubankova, where they had written a PRL paper just after during that time actually on what is called an interior gap superfluidity, and that looked to what I was doing in the quark matter. And Prashant quickly told me that let's quickly write a paper on this interior gap superfluidity in cold atoms, and that's how we jumped into it with Bimalendu Dev and Amrita Mishra. Myself, that was in 2004. And later on, Prashant was telling me that that is the first paper in India on cold atoms. I was quite amused. So after that, we looked into different aspects of it in the LOFF phase, that is the condensates having finite momentum, and also a BCS-BC crossover physics in relativistic system with my student Bhubaneswar. And recently, we are discussing about entanglement in brisk pair superfluidity and Fermi surface topology. That is with Rajrupa. Rajrupa is a Ph.D. student in IIT Bhilai, very bright student. Chandini is a faculty in Utkal University. And of course, Prashant and Shudhana Patra is also a professor in IIT Bhilai. So we are almost finalizing the manuscript. Hopefully, by end of this month, this will come into the light. So this title of the talk is superfluidity and quantum entanglement in that. So I will first discuss about superfluidity, particularly in cold atom case, and with a contact interaction. It's not working. So then I will try to take a variational answers for the structure of the ground state of this dense fermion system with attractive interaction, namely the BCS type of ground state, and see if the coupling is increased, how we see explicitly the BCS-BEC crossover. And I'll define what I mean by basic crossover physics there. And if the number density are different, there can be various interesting type of superfluid phases. Each of them I will classify. And then I will go to calculate entanglement entropy and the thermal entropy. What is the relation between them or how they are related? Those things I will try to explain. Finally, I will summarize and give an outlook. Let us see how far we are going. So, okay. Slide. A little bit of introduction. As we know from this conference, this meeting, quantum information theory is important for multitude of promising new applications like quantum communication, teleportation, quantum cryptography, and many more things. Also, we must note that even earlier time, the development of quantum mechanics time, entanglement played a key role, and not only for development but also for validation of quantum mechanics. It also plays a crucial role in quantum computing, where entangled qubits provide an exponential improvement over classical computers. So this is on the quantum mechanics. Lot of an entanglement, lot of work has been done, but the precise role played by entanglement in quantum field theory is still an open question, and it is kind of progressing. I mean, a lot of work is being done very recently. For example, entanglement of scalar field in an imaginary sphere with rest of the system, that implied the area law of black hole thermodynamics. There have been studies on the link between entanglement, quantum chaos, and thermalization. Also, the renormalization group flow people have analyzed recently, which connects the ultraviolet and infrared, low energy and high energy. The flow which connects these two cases can be understood as a momentum space entanglement between the degrees of freedom in the high energy and low energy case. And so the concept of entanglement in field theory is not just of academic interest, but also it can have important implications. People have recently tried to see in heavy ion collision context why the quark-gluon plasma thermalizes so quickly. In these theories, there is this theta vacuum, the theta vacuum of QCD. In strong field, you produce in strong electric field, you produce electron-positron pairs through a mechanism called Swinger mechanism. How does entropy plays in there, or how can you estimate entropy from the distribution of the particle, estimate entanglement entropy from the distribution function or its moments or the cumulants of the distribution function? You can connect it to the entanglement. So what I will do today, as I mentioned earlier, I will discuss the entanglement between Cooper pairs within the quantum field theory. As we know, Bardeen, Cooper, and Schrieffer formulated the so-called BCS theory of superconductivity, and the ground state was constructed as a collection of Cooper pairs. And these ideas have been applied to various systems like superfluidity in cold atoms. And in fact, this cold atom superfluidity is a highly controlled system where these experiments, you can control the number of particles they are forming pairs. You can control their strength of the interaction. You can make it attractive to repulsive to infinite interaction using the magnetic field and fastback resonance physics. I won't go into detail. But these are actually very interesting case that this has also implications in ultra-dense matter like quark matter in the core of neutron stars. As I was telling you, as the neutron stars are charge neutral objects, and superconductivity there occurs between up and down quarks, with spin up and spin down, different colors. It's a very interesting phase of quantum chromodynamics, where different types of superfluidity is in different classes of superfluidity is proposed, not seen, proposed. So some of these things, interestingly, can be connected to the cold atom superfluidity case, because you can control the number of atoms that pairs. So what I will focus today, as mentioned, on the entanglement entropy between fermion pairs in such Cooper paired atoms under various conditions like population imbalance, that is the number density imbalance, or as a function of the coupling. How do we define the entropy here, and how do we actually calculate here? I am also learning this subject. So a very interesting set of lectures was given by Dima Kharjiv. The reference is here at Poland, Kharkov School, and which connects between entanglement entropy, entanglement physics, quantum entanglement, and high energy physics are in theory. Beautiful set of lectures, very clear, and you can follow them. And this is another paper by Dima and Florio, Dima Kharjiv and Florio, about swinger pair production that I was referring to. So let's try to look at the cold atom physics. So consider just two species of non-relativistic fermions. Kind of, let's take them to the same mass also for simplicity. But two species in the sense you can distinguish them from the spin stuff. One will be spin up and spin down. That are the two species. Like the two hyperfine states of potassium 40 or lithium 6, and assume a point-like attractive interaction. So the first term is the Hamiltonian is this sum over A2 1 2 meaning that is the species in one for spin up, two for spin down. The first term is the usual non-relativistic kinetic term. The second one is the co-Fermi interaction, point interaction thing. Strength is depends upon coupling, decided by G. Okay? Like in field theory, you define a vacuum state. So this psi is an annihilation operator, which the vacuum is defined by such that psi on vacuum is 0. So A is the spin
any
index.
difference between psi subscript A and psi superscript A? Or they are
Sorry?
same?
Same.
Is there any difference between psi A in the subscript and psi and the superscript?
No, it is same thing. I think I'm being careless in typing it. It can be super. A essentially is the spin up or spin down. I think is ignore superscript or subscript. So yeah. So to construct the ground state, so let's call it an answers. We took is I call that state as state omega, which is exponential of pairs of these two particles, like spin up and spin down. Okay, so it is in the exponential. There are arbitrary number of pairs of spin up and spin down, and momentum k and minus k, and that distribution is given by Fk dk minus Hermitian conjugate acting on vacuum. So this omega, sorry, the factor half should be within the exponential. There is a error there. So it should be in the argument of exponential. And epsilon AB is a two-dimensional Levi-Strauss tensor. Nothing much. I mean, it ensures that spin up is with pairs is spin down or vice versa. It only indicates that. So this operator psi A on vacuum is 0, but since omega contains many pairs, psi on vacuum is not 0. There are many pairs. Exponentially large number of pairs are there. So one can define, on the other hand, once one realizes that this is a Bogoliubov transformation, one can define the psi prime operator, which is U psi U inverse. That will annihilate omega state. You can just substitute U psi U inverse acting on omega, because omega is U of on vacuum. So psi prime on omega, U inverse and U will cancel out, and psi on vacuum is 0. So that will end. See, if you substitute this thing here on this omega, so this will cancel out psi on vacuum. So one can define these operators, and one can expand, and you shall see this is a Bogoliubov transformation between psi prime operators, those operators which annihilate vacuum, and those operators which constitute the ground state, namely the BCS pairs. Okay? So one can actually then, if you want to do thermodynamics, one can use this technique of thermophile dynamics. There is another thermal Bogoliubov transformation. One can make it to have a finite temperature, finite density kind of ground state. I don't show in detail these things. They are there in those references, and you can check that. But having done that, what does this omega state tell us? If I calculate the psi expectation value, particle expectation value, it turns out that it is related to the same function of Fk that was appearing here through this sine 2 Fk, and the other functions that are theta. These are the thermal distribution functions. At 0 temperature, this won't be there, only this sine 2 Fk. On the other hand, the number density, which is psi dagger psi, will have a cos square Fk, sine square theta, and the particle A will have a component which depends upon the distribution function of that particle, and a component which is, because A is connected to B in the state, it will also depend upon the distribution of the other part. Okay? So at 0 temperature, sine square theta becomes 0, cos square theta becomes 1, and what you will have psi dagger psi is sine square F. That I emphasize because that will come again and again in our discussion later. Now one can, what is thermodynamic potential? It is the energy minus Ts minus mu n. That is the thermodynamic potential. Thermodynamic definition. And that is what energy is Hamiltonian expectation value, and mu times rho is the chemical potential for species A. Rho is its density, and S is the thermal entropy, which is related to the distribution functions. In fact, that is written as sine square theta, like distribution function is here sine square theta. Sine square theta log distribution function plus cos square theta log cos square theta. So there are, till now I have not specified what is Fk and what is theta. That you can determine actually by minimizing this thermodynamic potential. Minimize with respect to Fk and this theta. And what you get if you extremize the thermodynamic potential with respect to the function Fk, you get tan 2 Fk is g times this psi condensate expectation value, which I call as some delta, by epsilon bar minus nu bar, where epsilon bar is the average energy of the particle which condenses. Nu is the average chemical potential of the particles which condense. And this nu is actually related to the chemical potential mu A in the Hamiltonian or modulo. There is also a 0B. Because of the interaction, this is a rho 1, rho 2 kind of interaction. It's non-zero, that will go to other rho. Similarly, if we so if I substitute it, these solutions here in the G psi up sign down expectation value, explicitly it is in terms of sin square Fk. So it is kind of a self consistent equation, because delta is there on the left side and on the right side. The trivial solution is that delta equal to 0. There is no that. If you are interested, that is normal matter solution. So this is the superconducting gap is become superconducting, because you try to calculate what is the write down the dispersion relation, you won't have any zeros of the distribution function. Excitation energy will be at least delta. The minimal thing will be delta. On the other hand, if I try to extremize the thermal function theta A by this condition, then the theta A, sin square theta A, as I was telling, it is related to thermal distribution function, will have a thermal form, e raised to power beta omega A plus 1. But these omegas are not the average omega that we got here, but it is modified by this change in the chemical potential. Delta nu is the nu 1 minus nu 2. So the omega 1, particle 1 distribution function has the average one minus the chemical potential arising from the when there is not, the densities are not the same. The chemical potential should be different. So if it is so, I substitute these functions in the expression for the thermodynamic potential. So this becomes the thermodynamic potential, and this is kind of epsilon minus nu, epsilon bar minus nu bar minus omega bar. It's the normal matter minus the superconducting matter, that differentiation. Normal matter will have epsilon minus. And then this is the thermal part, the standard thing in StatMech you get. And this is the those 4 Fermi interaction part that you psi dagger psi, psi dagger psi. Psi psi will contribute, give a delta. Another psi dagger will give you a delta star. Okay. How this part is decreases with delta. This part increases with delta because G is negative, remembering that G. So if you vary with respect to delta, you will have a minimum. For a given coupling, you will have a minimum in the thermodynamic solution. That is the yeah. Like, yeah, it is standard volume term. I mean, yeah, I mean, sum over V you convert into d cube K. That comes in phase space form. And suppose I go to 0 temperature, distribution function will go to theta function. So your gap equation becomes like this. Because the delta here I have cancelled out. So, but this integral is of course divergent. So what does one do? One uses the SF scattering length of the atoms that one uses to regularize this integral. And this renormalized one is m by 4 pi as. S is the scattering length. Is related to this becomes finite if you subtract out this 3 part of the 3 part method. So what is the idea? So this is the gap equation, and this is essentially is the coupling, and then you try to solve this equation for a given coupling. Except that two things we don't know. One is these are functions of nu. The chemical potentials come into picture here. Chemical potentials we don't know. So those are determined by these two equations. Average density and the average difference in the density. This will determine what is delta nu bar. This will tell you what is nu bar, and that the other equation gives you delta. That for given rho bar, for given density difference, you know what is nu bar, what is delta nu, what is coupling. With this, you can calculate any coupling. So that is what I have to do. So what do you get? This is a case for the symmetric phase. By symmetric, I mean there is no chemical potential difference. Number densities are equal. In that case, this x-axis is a measure of coupling. This side, the negative coupling corresponds to the BCS phase. Positive side corresponds to the BEC phase. And this 0 corresponds to unitary limit. BCS to BEC crossover, and this how the delta changes. This is actually inverse of the coupling. KFA equal to 0 means coupling is infinity. 1 by KFA, KFA equal to infinity means infinity coupling. 1 by KFA is. So this is how the gap increases with increase in coupling from BCS to BEC. And as I said, you have to solve also for the chemical potentials. This is the chemical potential that solve interacting chemical potential. It decreases. It goes from positive to negative for certain chemical potential. It changes the sign of the chemical potential. That is a practical indicator of BEC crossover in BEC resin. The chemical potential becomes negative. So as you say, this the increase of the gap with coupling, the BCS side is exponential for small coupling. Then of course, it's not so fast. And those things can be analytically calculated. And we also try to see these are kind of KFA. A is the scattering length. 1 by KFA. Yeah, same is. Yeah. KFA. No, KF is the Fermi momentum. You have scaled it out. You have scaled it out. Yeah. That's the dimensionless coupling. I mean, sorry. that is just a scaling factor because these are dimensionless coupling. So now I come to if there is chemical potential difference, okay, or the number density difference. As I said, that's omega 1, 2 or AB that is related to omega bar plus minus delta. It may so happen that depending upon, and these are not free parameters. What is free is your rover, how much atom you are having, and what is the difference between the number density of them. That you can control. This comes out as an output. What is delta? What is delta nu? What is nu bar is your output. So it may so happen that this omega 1 or 2 can become 0. So solutions, the zeros of omega 1, 2 define the Fermi surface in the dispersion reduction. So the solutions of gap equation can have no Fermi surface, that is the usual BCS superfluidity. Nowhere the omega becomes 0. You need at least delta to excite something. Okay? In the omega versus k, if you plot, you need at least delta to excite the fermions. Depending upon the couplings, you can have one Fermi surface. This is what Wilczek called as interior gap superfluidity, in which the bigger number density thing Fermi sphere is there. Interior part of it, it is like a free T. Only at the boundary of the smaller number of pieces Fermi here, you have the super. Also, you can have two Fermi surfaces. To solve this, there will be some value of k. There is a k min to k max, between which it is like a normal matter. But in all these cases, delta is non-zero. So gapless modes means the gap can be non-zero, but the excitation energies can become zero. So, sorry. So this, what I told earlier, this is like species 1 dispersion relation. This is the species 2 dispersion relation, and this has the minimum delta that is the usual BCS phase, where the number densities are essentially the same. The blue one is the species 1, dashed one is the species 2. Is just for clarity, it is slightly shifted, but it's top of each other. So as I said, I mean, at zero temperature, what do you have usually for free fermions? You have either 0 or 1, right? Up to Kf, the Fermi momenta, everything is 1, the number density is 1, and beyond it, it is 0. When they are paired, near the Fermi surface, it deviates from 1, starts with 1, but it will deviate from it. And where it will be deviating will depend upon the. And it will for both the things. When there is single Fermi surface, this part is free, but from here onwards, both are paired. This is the single Fermi surface KFT. There can be two momentum in which the particle can have 0 from the dispersion relation. Between this and this, we have like a normal matter. So up to this, it is the densities are same. Here the particle species 1, like normal matter, goes to 1. And at that time, the second particle goes to 0. It continues up to certain point. And then again, they follow the BCS distribution function. So the number density difference essentially comes from rho 1 has 1 occupation number here. Rho 2 has 0 occupation number here. So if you integrate over all the k, there will be rho 1 minus 2. So two things. So this is an interesting case in the sense that such you can have number density difference, you can have a gap, but still you can have gapless modes. The excitation energy, if I hit it up, these modes will be excited more. So these things were interesting for quark stars or neutron stars, because if there are gapless modes, it will affect the decay of the particles, and like neutrino going away, neutrino scattering will be affected, because some of the quarks will have the quarks are gapped, but only some of them are not gapped, so they will go there. So there will be the dominant mode of cooling. So that was the one example of. So yeah, yeah. It will be on the top, I think. Yeah. Dash one. Yeah, this is not plotted here. I'll show you what it is. Space, I think. That no. Gap is this is the gap. This is the one. If we plot with that gap, the distribution functions will follow this, and then there will be at certain k, it will go to 1. This will be the second one will go to 0. Just like normal Fermi matter. Fermi distribution function is 1 for normal thing when occupied, and 0 beyond k. Okay? So that is what it is. Between this and this, in the dispersion relation, delta is non-zero. Come back to. Now I will try to. So much for the different phases of superfluid phases, BCS phase, the IG phase, and the Briest pairing phase. One with 0 Fermi surface, 1 Fermi surface, and Fermi surface. Now let us let's look at the entropy of the BCS state. As I had done earlier, psi dagger psi was in terms of these functions, the condensate functions Fk and the distribution function. Whereas we evaluated, minimizing thermodynamic potential, this becomes this, and sin square F becomes this, where omega bar is delta square plus epsilon bar minus nu bar square. And so if I consider just the symmetric case, for symmetric matter, there is no delta nu part, so that won't be there. And what we will have is just the sin square d cube at 0 temperature. Okay. Now sin square. So if psi dagger psi 1 dagger psi 1 is sin square Fk d cube k, then sin square Fk is the probability of having species 1, or if it is 2 case, it is 2, with momentum k or minus k. If this is a probability, one can associate a entropy, the Gibbs entropy, to the system by counting the microstates. Because these are fermions, for each momentum you can associate only one particle. Okay? And sorry. Because these are fermions, one particle per momentum will be excited. Sin square F was the probability of finding the particle F exciting in momentum K. Cos square F is, it is not excited. So sin square F n ln n plus n 1 minus n ln 1 minus n. This is essentially counting the number of states possible, and every momentum is either excited or not. So this is the Gibbs entropy. We're counting the number of states. But what I will next try to show is that this Gibbs entropy has an origin from the entanglement entropy. What is entanglement entropy? Let me try to answer that in the context of superconductivity, superfluidity. So it is, you already probably know this thing. Consider a pure state. A state is defined in a Hilbert space. So suppose this Hilbert space is bipartite. There are two subsystems. Okay? So H is written. I'll just take 10 more minutes. Is that okay? So the global pure. Yeah.
Yeah.
Okay. So this Hilbert space can be written as some Hs and direct product of H. It's a direct product space. Now a subsystem S is defined by taking a trace over S over this E subsystem. Will define what is reduced density. So even though the psi is a pure state, in S rho square, rho square is rho, the density matrix. After tracing out, this rho S is not a pure state. There will be some mixed information. So even though psi is pure state, rho S is a mixed. Whenever S and E are entangled, this mixedness encapsulates the information about S in the bigger in this system S that is inaccessible without access to E. And von Neumann entropy, the entanglement entropy, which is minus trace of rho S, the reduced matrix rho S and ln rho S, that quantifies the degree of entanglement between system S, subsystem S and subsystem. These things probably you have were aware many times. So if it is a pure global quantum state, the bigger state is a pure state, then the subsystem entropy satisfies these two conditions. The entropy of rho S is same. And because both this entanglement entropy measures the shared quantum coefficient. Because this entropy, since this is a pure state, so this will have the same eigenvalues for the reduced density matrix. Now this is fine, but actual calculation, how do I do for the BCS ground state? I know there is a ground state I have defined. How do you calculate explicitly the entropies, the entanglement entropies? Okay. So just recall this omega was in terms of a pair operator. B dagger K is psi dagger psi 1 dagger, psi 2 dagger. The pair operator Fk and Hermitian conjugate. I want to write it in a different way. Which way? There is an exponential and it is a sum over all the k's are there. Right? Exponential sum, I can write it as product of. If I do that, So each is product of K, omega K. And this, if I do little bit of algebra, this omega K, each of this omega K can be written as cosine of Fk, sine of Fk with the two operators. Okay? Little algebra is there, but it can be written this way, which I don't want to write cos F, sin F always. I write it in the more familiar language of superconductivity. It is UK and VK. So here, let us identify there are two subsystems. One is the spin up with momentum K. The other subsystem is spin down and momentum minus K. Okay? So local Hilbert space is a tensor product of two single mode Fock spaces. These are occupational number space. So this vacuum state is what? Vacuum state is nothing occupied in the K up subspace, nothing occupied in the K down, minus K down subspace. So this I call it 0 here and 0 here, write it as 0, 0. Okay. So similarly, I define this doubly occupied state where this pair acting on this 0, 0. This creates a one state with spin K, spin up, and spin down, and momentum minus K. This I denote as 1, 1. So I should be clear about my notations. Therefore, this omega K is UK 0, 0, VK 1, 1 in this two Hilbert space description. Right? Now I have to define somehow the density matrix for the each K mode. So how do I describe the density matrix? The standard definition, omega K. Okay. What is omega K? This is UK 0, 0, VK 1, 1, and omega bra is UK star 0, 0. So I take in this occupation number basis, I just take a direct product where I have the basis vectors are 0, 0, 1, 1 that I have, but I can also have 0, 1, 1, 0, 0, 1, 1, 0. So I just multiply it. What I will have is this matrix. Just you do a direct product of the matrices, you will get it. Okay. So one kind of problem I tell you is to show that this is a pure state. What is a pure state? Square should be same as rho, right? That is the definition of a pure state. So your BCS state written in terms of this occupation number basis, the density matrix becomes a pure state. So long as this UK square plus VK square is 1. You can check it. Take rho square of this matrix, use that relation. So this is a pure state. As I said, you have to project out a certain part of it to know the density matrix, right? How do I do the projection? By taking a partial trace. Okay. So how do I do the partial trace? So this was my K minus K bigger matrix. Okay. The first index is K occupancy, second index is minus K occupancy. Okay. So this is a 2 cross 2 and 2 cross 2. It's a 4 cross 4 matrix. I have to trace out, say, this minus K. So I have to trace out over J and L, written as red color. Okay. How do I do it? You just find out the IK element and here JL. So this will not be a 4x4 matrix. It will only have I and K. A 2x2. Right? So rho K is trace of the minus K states. Other Hilbert. K minus K, where J and L are the same. That will give me the IK element. And what exactly it is? Rho IK, IL, KL. Okay. What you get is mod UK square, VK square, simple 2x2 matrix. Simple. I mean, nothing very complicated idea. And the entangled entropy of the reduced matrix for each K is what I said. The entanglement is minus UK square ln UK square plus VK square ln VK square. And since it's a trace, you have to take also the integrate over all the momentum modes so that the entanglement entropy SE is an integration of all. Okay. So look what you get. You get this thing. If you have U as cos square F and V is sin F, then that is actually is the other entropy. I mean the Gibbs entropy that we had derived earlier by counting the number of states per moment. So the Gibbs entropy here arises from a more fundamental level from the entanglement of the BCS. That is very interesting for to note, and so much so. So let's see how much. What is the hello?
Yeah, now you
Yeah,
can hear.
Okay. All okay. All that I was telling is that if I take the symmetric case, no difference in no density difference. The rho K, which is this structure, is given by the left side of the figure as a function of K. Corresponding entropy is given in this right side. And as you can notice, the entropy has the entanglement entropy has a peak, and that corresponds to epsilon equal to nu, that is at the Fermi surface. And at that point, it is a Bell state. Because you can see that rho K, which was 1/2, so the corresponding cos theta, I mean cos F is 1/√2. So 1/√2 0 0 plus 1 1, which is a Bell state. So one can identify this way the deeper origin of Gibbs entropy from the entanglement perspective. What happens when there is a mismatch in the Fermi momenta? So here is the case at 0 temperature. So this part is the top left part is the left side is the density distribution. Right side is the entanglement entropy. So this is the blue one tells you the spin up, and red down is spin down or particle B. And for without loss of generality, we assume that the rho A is more. So this is 1 here, and this is 0 between this momenta. Okay. If I calculate the entropy density as a function of K,
Able to hear you, sir. Not audible.
Yeah. Okay. Yeah.
Yeah, fine.
Yeah. Okay. So left side is the density distribution. As these have different in density. Without loss of generality, we take rho A to be of higher density and rho B of smaller density. So rho A in certain momentum range becomes like rho A becomes 1 and rho B becomes 0. So that between these two momenta, K min and K max, the system behaves like normal method. And the right side is the entropy as a function of K, Sk, entropy distribution. And you can see that between K min and K max, the entropy for the normal.
To hear you.
Hello.
Yes.
Is it?
Yeah.
Am I audible?
Yeah. Yeah, it's better.
Okay. Okay. Thanks. Yeah. I am audible now.
Yes.
Yes.
Okay. Okay. Good. This is a better. Yeah. So this is the second. How much time I have? I'll take 2-3 minutes.
Yeah.
Or 2 minutes.
I think, yeah. Just 1 hour over. Yeah.
Okay. 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 So these are the finite temperature results where the sharp drop of entropy gets modified due to temperature effect, and that is what I wanted to show. So these are the parameters for this wrist pairing case, but let me summarize. So what we did is very simple. We considered a variational method using a BCS type of ground state to discuss the crossover physics for cold fermionic atom system. And this condensate function, then the thermal distribution functions were determined variationally by minimizing the thermodynamic potential. And we saw that different types of superfluid phases, namely the BCS superfluid, interior gap superfluid, or wrist pairing superfluid, corresponding to 0 or 1 or 2 Fermi surfaces are possible depending upon the coupling strength and the population density difference between the two species. We also calculated the Gibbs entropy by counting the microstates. Then we looked into the BCS mechanism from a quantum informatics viewpoint and estimated the entanglement entropy. The Gibbs entropy arises from the entanglement of the two species forming the pair. And when you consider for wrist pair, a non-trivial structure for the entangled entropy is observed for the wrist pairing superfluid. So entanglement entropy measures the correlation between two parts of a bipartite system, and Bogoliubov transformations reveals this entanglement between two components, which is not transparent for the BCS pair. So it will be interesting to figure out entanglement entropy for this crossover region, and particularly at the unitary limit. And one must take into account the quantum fluctuation, particularly near very strong coupling or the unitarity limit, whether there is a conformality in the system, what happens to the entanglement entropy near conformal limit. These are some of the open questions that one would like to explore. So I will stop here. Thank you.
Thank you so much for this very nice talk. 1 or 2 quick questions.